Here's the last section, section 6.3, volumes by shells. As I mentioned in the previous video, this gives us a method to find the volume of a revolution around the y-axis. Around the y-axis. A lot easier way of doing it than doing the disk method because we have to solve for the function in terms of y. That could be difficult to do. So the shell method. What the shell method is saying is the volume of the solid obtained by rotating a region under the curve y equals f of x about the y-axis from a to b, where a is less than b but greater than 0. So that means your interval is always from a to b in the positive direction. Is the volume is equal to the sum, there's a limit here, and goes to infinity of I equals 1 to n of 2 pi x sub I f of x sub I delta x, which is just the integral, there's a 2 pi out front, from a to b of x times f of x dx. All you're doing here is you take whatever your function is, you multiply by x, then integrate. A little bit easier than squaring things. So the idea behind this method is if I were to have some shape and I wanted to revolve it around the y-axis from A to B, the shape that we would get would be something like this. There's a hole in the middle. And it's going to look something like that. Okay, revolving around, right there's the y-axis. I guess this isn't as big. Something like that. Okay? And how this works is, imagine taking a little disc, a little rectangle, and revolving it around the y-axis. What you're going to do is you're going to end up with the shell. And then you move a little bit more, you end up with another shell. That's what these are saying. They're shells. Okay? Let's look at this formula. This says 2 pi. This is the radius times the height. This right here, 2 pi times, 2 pi RH. This is the surface area of a cylinder. If I have a cylinder of radius r and height h, this is going to give me the area on the outside, not the total surface area. We're not counting these circular regions right here. That's just, if I were to cut this and lay this out like this, it'd be a rectangle. Well, I've got some h and I've got 2 pi r down, h here. 2 pi r right there. So that's the area of this entire shell, and we're adding up all the shells. If you're looking at my notes, you could get a lot better picture of what I'm trying to get across to you right here. Also, if you look in the book, they're going to give you a lot better picture of what I'm trying to draw for you, okay? That's where I got the picture on my notes from the book. Now, you can also do the shell method around the x-axis. It's very similar. It's 2 pi y times f of y. It's the integral. But let's just jump straight into examples. This is a lot like the disk method, just a slightly different formula. So y is equal to cube root of x. Y is equal to 0. X is equal to 1. And about x-axis. Looks something like that. Cube root of x from y equals 0 to x equals 1, and I'm revolving it around the x-axis. So I'm taking a little shell like that. That'd be my outer shell, and revolving it and moving in. So this goes from 0 to 1. This is the integral from 0 to 1, 2 pi out front. x times f of x. Well, x times the cube root of x. Well, that's just 2 pi times the integral from 0 to 1 of x to the 4/3 power dx. I forgot my dx over here. This is to the first power. This is x to the 1/3 power. Add the powers together, you get 4/3. So this is 2 pi times 3/7 x to the 7/3 evaluated from 0 to 1. Plugging in 0 is not going to do anything. Plugging in 1 is just going to give me 3/7. So 3/7 times 2 pi is 6 pi over 7. If I were to draw this, what this would look like, where, let's see, it comes down to a point, something like that, where up here is circular, and down here it's got a circular base. Something like that. Now, this was doing the shell method. We could have done the disk method. Let's remember our answer was 6 pi over 7. 6 pi over 7. What I can do is rewrite this equation in terms of x. X is equal to y cubed. It's still the same picture, but now I'm revolving around the x-axis, which should be the integral 0 to 1. This is using the disk method. Okay? The disk method, f of y squared dy from a to b with the pi out front. Okay? I'm just illustrating you could get the same answer by doing the disk method. So all this is going to be is y cubed squared dy. Give me one moment. Where'd they go? Oh, my apologies. Let's put that graph back up here real quick. We're gonna have to do the washer method if we're using the disk method here. The graph looks something like this. So x equals 1 is the outer function, and y cubed is the inner function. So when we do this integral, it's gonna go from 0 to 1 right there. We're gonna have a pi out front, but it's gonna be the outer function squared minus the inner function squared dy. I almost made a mistake there. As you can see, it's vastly different if we're doing the disk method. So our answer before was 6 pi over 7. Let's see what we get over here. It should come out to be the same answer. So we get y, if we, oh sorry, not y, 1 minus y to the 6th dy, integral with the pi out front from 0 to 1. This is y minus 1/7 y with a pi out front evaluated from 0 to 1. If I plug in 1, I get 1 minus 1/7, which is 6/7, and I'm multiplying it by a pi. No surprise that it came out to be the same answer. So when to use the disk method as opposed to the shell method? If they're telling you to revolve it around the x-axis and you have a function of x, use the disk method. If you have a function of x and they're telling you to revolve it around the, sorry, I said that backwards here. Let me write it up. If you have a function of x and revolve around y-axis, use disk method. If f of x, if you have a function of x and revolve around x-axis, use shell method. Now notice, you got a function of x, you're revolving around the y-axis. They're different. Disk method. You got a function of x, you're revolving around the x-axis, or sorry, let's see. I knew that didn't sound right. There we go. If you have a function of x and you're revolving around the x-axis, use the disk method. When they're the same, use the disk method. If you have a function of x and you're asked to revolve it around the y-axis, use the shell method. It would be easier. Otherwise, you got to solve this in terms of y and then do the disk method, which again, that could be a pain. So this also works. If you have a function of y and you're being told to revolve around the y-axis, you should use the disk method. If you have a function of y and you're told to revolve around the x-axis, you should use the shell method. Okay, so that's just a little tip. Let's do some more examples. Final 3 examples of the semester. It says y is equal to 4x minus x squared. Y is equal to x. Let's see, x is equal to 1, x equal to 2, and it says about y-axis. See, my computer's telling me my storage is almost full, so if the video cuts out for any reason, I apologize. Let's see, 1, 2, 3, 4. Looks something like that. But we're only going from 1 to 2. Y equals x. Looks something like that. So we actually don't need any of this. That is the shape that we're revolving around. So, actually from 1 to 2. So, right there. Right here is 4x minus x squared. Down here is just x. We're revolving this around the y-axis. And to do this, when you have a function here, this is only going to affect the height. So you do the upper minus the lower. So this is going to be the integral from 1 to 2. We've got the 2 pi out front, x times the upper height minus the lower height. 4 minus x squared minus x dx. Well, we've got 2 pi out here. If I were to multiply this x through, you get 4x minus x squared minus x cubed dx. 2 pi times 2x squared minus 1/3 x cubed minus 1/4 x to the 4th, evaluated from 1 to 2. Now, if you were to plug in 2 into here, and you were to plug in 1 into there, and you were to subtract their values and multiply by 2 pi, I get 26 over 4 pi. To do this, I'm using my calculator, okay? That's a lot of fractions to keep track of. If I plug in 2, let's see, 8 minus 8/3. If I plug in, that comes out pretty easy. But plug in 1, I get 1/3, I get a 1/4. So I'm plugging this entirely into my calculator. I plug in 2, so plug in 2 into here, using parentheses minus, using parentheses, plug in 1. Okay? Make sure you use parentheses around the entire thing because this minus sign has to distribute. Okay, that's very important there. So we get an answer of 26 over 4 pi. Let's do another example. X is equal to negative 3y squared plus 12y minus 9, x equals 0. about x-axis. Alright, so this is a function of y. Let's go ahead and give this a quick sketch. X equals 0 is right here. This is a negative parabola, and it goes something like that. Now, if you were to solve where it crosses the y-axis, it crosses at 1 and 3. How I get that, you just take this function right here, set it equal to 0, and factor. If you factor, you get y minus 3 and a y minus 1 equals 0. I just did that really quick for you guys, but if you were to divide everything by negative 3 and factor, that is what you get. So you get y is equal to 3 and y is equal to 1. So it's this right here that we're revolving around the x-axis. So this would be my little shell right there. The shell is going to change as I change my radius. Revolving around the x-axis, I got a function of y, integral from 1 to 3 of y, f of y, dy, and I've got a 2 pi out front. So if you notice, they are opposites of each other. I'm revolving around the x-axis. I've got a function of y. I should use the shell method. I could use the disk method and get the same exact answer. However, if I were to try to solve for y in here, get y equals a function of x, it's not going to happen. I'm not going to be able to find y is equal to a function of x here. Okay? So I get the integral 2 pi out here from 1 to 3 of y times my function here. Negative 3y squared plus 12y minus 9 dy, which is equal to 2 pi times the integral from 1 to 2. Just distribute the y all the way through. Negative 3y cubed plus 12y squared minus 9y dy. Coming over here, 2 pi times, integrate, negative 3/4 y to the 4th plus y cubed, there's a 4 out front, minus 9/2 y squared, evaluated from 1 to 3. I have a 2 up here. I don't know why I have a 2 up there. It should be from 1 to 3. Again, plugging everything in, plugging in 3, plugging in 1, you get 16 pi. I know I'm skipping the evaluations, but I trust that you guys can punch these numbers in correctly on your calculator. Again, give it a look through. Make sure you're punching it in correctly. I know on the homework solution, there's a couple that you guys have already emailed me about. I accidentally punched in the wrong numbers. I should have made sure. Let's go ahead and do one more example. When we did the disk method, the very last example that we did was revolving it around a different line. This next example is going to be very similar. Y is equal to 4x minus x squared. Y is equal to 3, and we're revolving it about x is equal to 1. We're revolving that little shaded piece right there about this line, x equals 1. So, if I were to plug 1 in there, you do get 3. If I were to plug 3 into there, it's a little off, you get 3. Now, to take care of this, recall when we do these integrals, it's from 2 pi from a to b of x times f of x. These heights are going to be the same no matter what, so this doesn't change. It's this piece that's going to change. This is the radius. When we said 2 pi r h was our f of x, and our radius was always x because we're creating shells. This is the radius of the shell. Now, since we're shifted over 1, everything's going to be shifted over 1. This is no longer an x. Really what this looks like when you're revolving it around the x-axis is x minus 0 times f of x dx. But the 0 doesn't do anything. So that's why, we don't write it. So this is when you're revolving. I guess you could put a C here. When you're revolving around a line other than the x-axis, it's going to be x minus whatever number we are revolving around. So this is going to be 2 pi integral from 1 to 3 of x minus 1 times 4x minus x squared dx. There's our integral right there. Now, if you were to multiply that out, I do have it really quickly for you, so you don't have to actually go through that multiplication. You get negative x cubed plus 4x squared minus... Oh, I'm giving you a... I looked at the wrong line. Giving you an unsimplified form. You get 3 minus 7x plus 5x squared minus x cubed dx. So integrating this, let's see, you get 3x minus 7 halves x squared plus 5/3 x cubed minus 1/4 x to the 4th. Evaluated from 1 to 3. Again, I'm plugging this straight into my calculator. I plug in 3, get a number. Plug in 1, get a number. Subtract those two numbers, doing the upper limit minus the lower limit. And then I'm multiplying it by 2 pi. And you get 8 over 3 pi. And that would be your final answer. So when you're revolving around a different line, what you have to do is you have to take into account this shift. That's all this is doing, is shifting the graph. Where is it shifting it to? It's centering it at 1.